Alright, if I remember correctly, in our last class we completed up to register indirect addressing mode, where we learned that we can use two registers, R0 and R1, to behave as a pointer to an address where the data is stored. And when we need a 16-bit pointer instead of R0 and R1, we can use DPTR as a register. So now let us move on to the next one, next in addressing mode, which is indexed addressing mode. And I will ask you to please pay attention. Anyone saying anything? Right, so look at this addressing mode. Over here, I mean this addressing mode, that is index addressing mode, we only use when we want to access the ROM space in 8051. And if you remember, we normally store codes in the ROM space. Our codes are stored in the ROM space. In that case only we use move C or index addressing mode, and you can see the instruction itself is different. So far we used to use the instruction move only, but now instead of move we have to use move C. So this instruction specifically means that you are trying to access the ROM space of the 8051. Now look at the syntax. You will always move the data into register A or into accumulator. Instead of this A, you cannot use any other register. Then when you write @A plus DPTR, then they combinedly store the address of the location from where you are trying to fetch the data. Say for example, in an example, your DPTR contains the value 04308, and say your accumulator contains 028. If this is the case, your combined address will be, what will be the combined address? Tell me.
432H.
Exactly. So your combined address will be 04328. So whatever is there in this memory location will be transferred to the accumulator. That is exactly what is said in the comment section. Copy the content of the memory location addressed by A plus DPTR to the accumulator. Of course, we will see an example with this instruction, but for the timing, have you understood up to this?
Sir, it is slightly similar to the previous one that we did with the pointer one, right?
Of course, that is I mean, almost similar. The only difference is now we use the ROM space. The pointer is different, and we always need to store in the accumulator. Previously, you can use any register to store whatever is being pointed by R0 and R1. But over here, you have to use the accumulator. That is the only difference, nothing else.
Sir, is it a 1 byte instruction?
Yes, it is. I mean, are you asking about the opcode of this instruction?
No, sir, about the move C, sir, the move.
Yeah. 1 byte means, are you trying to know what is there in this address location?
Sir, after operating these commands, sir, what will be the next, sir? We'll use in the while we count the cycles.
Oh, you're talking, yeah, exactly. So you're talking about the opcode, right?
Yes, sir.
It is, we are not actually bothered about how many byte instruction this is. So it is not actually necessary. When the examples that we saw in the previous chapter, in chapter 3 of not 4, in chapter 3, only those instructions you need to know the opcode. Otherwise, I mean, you need to know how many bytes are there. But for instructions like this, it is not needed, but still in the appendix you can see. The appendix is there, right? In the appendix, it is given what is the size of the instruction of this opcode. You can see from their appendix if you want.
Okay, sir.
All right, anything else?
Sir, you are saying that in the destination for move C, it will always be the accumulator, right?
Right.
And as for the second portion, at the rate A, here can I write B or any
No,
other
no, no.
register in place of A?
No, you cannot write. This has to be A and BPTR. This is constant.
Okay.
Any other question, anyone? Okay, let us see an example. Okay, if you still have question, you can ask after that. So let's see an example. This is example 5.7 of the book. Let me write the question as well. So the question says, let's just assume that starting from this address, that is 258. Starting from this address 258 in the ROM, we have got something like this. I mean, within double quotation, we have got this AMERIC America. Our target is we need to transfer all these data which started from 258 into RAM locations starting from 48. Is the question understood?
Yes, sir.
Is the question understood to all of you?
Sir, can you repeat?
No, sir.
Look at the question. The question says, assume that ROM space starting at 258 contains America. I mean, that means from this address, that is 258, America is stored. That means in 250H exactly, you have got the ASCII of A. In 251H, you have got the ASCII of M. Then in 252, you have got the ASCII of E and so on. Your target is write a program to transfer the bytes into RAM locations starting at 48. That means whatever you had in 258 should be transferred to 48. Then whatever you had in 251H should be transferred to 41H and so on. So did you understand now the question?
Yes,
let
sir.
me now give you the solution. After that, I'll explain it. It is there in the book. If you want, you may write. Right, so now let us look at the solution. We start with origin 0, 0. It has nothing to explain over here. Now the next line, move data pointer, comma, hashtag my data. So you already know when we write move data pointer, comma, hashtag my data, the value of the address will go to the DPTR. That means after line 2, initially your DPTR will contain the address of the label. So what will be the value of DPTR after the second line?
So 250H.
Right, it will be 250H. Then you move 40H to R0. Why? Because this is your starting address. So that starting address you are moving to R0, your target will be, you will use R0 as a pointer. So that's why you are storing the first address in the RAM location into R0. Next we move 7 to R2. Why are we moving 7? Because you count over here, you have got exactly 7 letters or 7 characters. That's why we move 7 to the register R2. So let's write the initial values. Initially your R0 contains 40H and your R2 contains 7. Now enter over here, clearing your accumulator. All right, so move C A at the rate A plus DPTR. So in this line, what is the address that will be formed? A is 0, DPTR is 250. So the address that will be formed is 250H, right?
Yes, sir.
And what is there in 250H? The ASCII of capital A. So you are moving the ASCII of capital A to this accumulator. Then you are writing move at the rate R0, comma A. That means go to the address contained by R0. So what your R0 contains? 40H. So in the address 40H, what are you moving? Whatever is there in A. What is there in A? In A, we have got the ASCII of capital A. So we have successfully done that. Now we are incrementing DPTR. That means your DPTR now becomes 251H. You are increasing your R0 as well. So R0 becomes 41H. Now you're decreasing your R2. So R2 becomes 6. If it is not 0, you jump to this label again, that is back. What you do again, you clear your A register, because if you try to recall, your A register, if you do not clear, contained the ASCII of A. So your address will be disrupted if you do not clear this register. So we clear this register. Now we write move CA at A plus DPTR. So now what is the address that is being formed by this instruction?
251H.
Exactly, 251H. So what is in 251H? ASCII of small m. Then you move that to the address held by R0. R0 contains 41. So in 41H, we move the ASCII of small m. And this process is repeated until you finish transferring all the data.
Sir, can you repeat the last part a little bit?
Last, which portion?
Sir, after we run the first loop, we get A, the ASCII code of A. Then you said we have to clear A. Why do you need to clear A?
Because A already contains some value, right? Those values are in binary. So if you do not clear register A, when you come over here, those values will be added with DPTR to form the address. But you do not want that. You want to move on to 251H, right?
Yes, sir.
But if you do not clear your register A, then whatever is there in register A, that will be hexadecimally added with DPTR to form the address.
Okay, sir. Got it.
Yeah, so that's why we clear this A register. Any other question over here?
Sir, we could have written the same program using register indirect address. I mean, what is the role of A in the move C? I mean, that's always, we are always clearing A. So it's always 0 in case when it's being added to DPTR. We could have written move A, comma, at the DPTR just. I mean, the previous
You
method.
could have written, yeah, move A, comma, at the rate DPTR. You are right. But in that case, you could not have used this C. You see, there is a C part at the end of this instruction.
Yes, sir, but our code would have worked, right?
The code would have worked, you are right over there, but when the syntax has been made, they made it like this, that it has to be move C and A plus DPTR. Actually, there is a significance of this A. In this example, you are clearing A every time. That does not mean every time, in all the cases, you will clear your A register. You can have values in A register that you will utilize. You will see in the next examples.
Okay.
Any other question? Okay. Now let me.
Second line,
Hmm.
it is move dptr comma hash my data.
Yeah.
So sir, in the place of hash my data, shouldn't there be the ASCII of A?
No. Your my data contains this address only. It does not contain what is there in this address. In this address, I mean, in this address, ASCII of A is there. But your my data label contains only this address. It does not contain both the things.
Sir, move dptr hashtag 250h and then db America. We could have written it like that as well instead
of my data. Yeah, you could have, instead of this line, you could have simply written hashtag 250h. It will give you the exact same result. Let me show you a little bit different thing. The code will be same. I will rewrite this code in a little bit different way. Okay, I don't need this line. All this will be there. And this line. I will rewrite the same code, okay, just in a different way. So the first three lines will be there. That is your origin will be there, dptr my data is there, R040H will be there. Here will always be there. A plus B. Okay, you get this right? dptr. New line will be here. That is one new line. That is jump 0 here will come. Then all other things will remain as it is. R0 short term thing. Alright, now look at this code. So what is the only change that we brought? Initially over here we had a register that counted how many bytes of data we need to transfer. But now we removed that line. That line is not there. Instead of that, we intentionally added a null character at the end of our data. And this line is extra. So if you remember, JZ means jump if accumulator is equal to 0, and this is most probably given in your table 3.1 of chapter 3. So the same thing, every time you will move the data to the accumulator, but before transferring that data into RAM location, you will check whether accumulator contains a null character or not. If the accumulator contains a null character, you will directly jump over here. That means you will not perform these instructions. Until and unless you encounter a null character, you will keep executing all these instructions. And the null character will only appear after you have transferred all this data. So both of these codes will give you the exact same result. The only difference, in the previous example, you had to know how many data you are, how many bytes of data you are transferring. And in this example, you don't need to do that, but you need to add an extra 0 or null character at the end of your data. Any question over here up to this?
The sjump here, what is the function of this line?
It means that stay in this loop indefinitely. You'll see most of the codes that we write in microcontroller, it is designed that to stay in a specific loop forever until and unless some external pulse is given or something like that. So this, after you have transferred all the data, your processor will remain in this loop until and unless you do something. Either you reset, turn it off, or turn it on, or you can modify this code as well. That doesn't matter. Say you can overwrite over here, say CON. You can make another level, and instead of here, you can write CON. So what will happen after finishing? It will jump in this level and it will end the code. That is totally up to you. These are part of data. The main target is to explain you how things are working. Is it okay?
Yes, sir.
Any other question, anyone?
So sir, basically when encountering the null value, the dptr will become 0.
No. Why will the DPTR say? DPTR will contain the address. DPTR does not depend on all this data. DPTR will just contain the address. Every time you will increase the DPTR, so DPTR will keep on increasing from 251 to 34. Finally, when you go to 257H, you will see that your 257H contains zero or null character. So this value will be transferred to the accumulator. Then in this line, you will check whether what your accumulator contains. Your DPTR will always contain these addresses. It will not contain these values. Did you get your answer?
Yes, sir.
Any other question, anyone? Okay, let's move forward. So we have already finished all the 5 addressing mode. There are a few other things that we just need to finish. Let me explain this lookup table using an example. I think it will be better. Again, this is example 5.8 of your book. I think if the examples are not different in different versions. If you want, you may write. If you don't want, you may not write as well. Let me write the question briefly. So please look at the code. First of all, see the question. The question says get X from port 1 and send X squared to port 2. And the condition given is X will be from 0 to 9. So this is just a second. So the code says, problem says get X from P1 and send X square to P2. So now look at the code. First line is simple. Move DPTR is 300H. All right. So we are storing 300H in DPTR directly. Before we go rest over there, look at the right hand side. So this is your origin 300H. So in 300H, tell me what is there? What is stored in 300H?
0.
0. In 301H, what is stored?
So 1.
Exactly. So let's write a few, not all. Then we'll have 4. Then in 303H, we'll have 9. In 304H, we'll have 16. In 5H, we'll have 25, and so on. So you get the idea how this memory is arranged, right? Then we move FFH to A, and then we move that to port 1. This is simply to make port 1 as input. If you remember, we need to send 1 to the ports to make sure that port 1 or that specific port acts as input. That's why we send FFH. Instead of these two lines, you could have simply written move P1, 0 FFH. This will also give you the exact same result. Now come over here. Move A, P1. That means from P1 you will get the value of X, and it is already given that X will be from 0 to 9. Assume from P1 you are getting say 3. So what is there in A? If P1 is giving 3, what is there in A?
3.
9.
No, A will contain 3. Why 9? You are moving the exact same value from port 1 to A, right? So you will get 3. All right. Now look at this address. Your A contains 3, your DPTR contains 300. So in which address will you go?
303.
Exactly, you will go in this address. What is there in this address? 9, right?
Yes, sir.
So now you are moving 9 in the accumulator. That 9 you are moving to P2 and then you are going back. Again, you are trying to get input from P1. So assume now your P1 contains 5. So you are giving 5 to A. So what is there in A now? Now A contains 5. So what is the address? The address becomes 305. If you go to 305, you see you have got 25. So 25 is sent back to P2. And thus, without doing the actual mathematical calculation of squaring the numbers, you are using a simple lookup table from where, and you have designed the lookup table in such a way that every time whatever you get from P1, the square of that value you will be able to send to P2. That is how you have designed your lookup table. So is there any confusion over here?
Sir, when did you insert the values of table in P1?
I never inserted the values of table in P1.
Yes, so how did P1 get the value 0149? So far,
P1 got the value 0149. All these values are actually not in P1. All these values are from here. These values are stored from this memory location onward. See, in 308 we have stored 0. In this memory location we have stored 1, right?
sir, let me, sir, here you said suppose P1 contains 3. Where is P1 getting the value 3 from?
P1 not contains. See, you are making P1 act as an
input,
right? That means what? P1 is definitely connected to some device. From that device, P1 will take input, right? That means P1 is getting all its data from the connected device. Is it okay now?
Yes, sir.
All right. Any other question, anyone?
Sorry, in here, P2 is working as output or input?
P2 is definitely working as output because you are sending something to port 2. That means that data you are again sending out from P2. So P2 is working as output.
Sir, configure it as output.
Yeah, you may configure it as output as well. Again, I'm saying these are not complete codes. Okay, the main focus over here was on the lookup table to explain you how the lookup table works. But if you go for the complete code, definitely you need to configure P2 as output as well.
Sir, in case of questions, do we need to build the lookup table by ourselves? I mean, it's x square for this, but it can be x cube. And
it can be x cube, definitely.
So we need to build our own lookup table.
Yeah, that is the only thing you need to do. The rest of the things are very straightforward.
Okay, sir.
Any other question, anyone?
Sir.
Say anyone, say.
Sir, don't we need to clear the accumulator?
No, because every time in this line your accumulator is being overwritten. Even if you clear, that is a good practice. Even if you don't clear, that is also fine. So after this line, you can simply write clear accumulator. I mean, it is better. Even if you don't write, it will not be a big problem. Because every time, see, from P1, whatever you had in accumulator will be overwritten. Because every time you are getting input from P1. But if you want, you can write over here, clear A. You can do that. Any other question?
Sir, you are saying that move A, P1. So the code doesn't bother about from which pin it was getting the value 3 or 5 or something.
No. In order to get a value like this, 3 or 5, you need all the 8 bits. It is a byte operation. This is not a bit operation. This is a byte operation. When I say port 1, I mean all the 8 pins of port 1 will be acting. Is it okay?
So to represent 3, I need only 4 bytes.
Yeah, you need only 4 bytes, but your instruction will actually be 00000110, I guess. 110 ki 3 na ki na? What is the binary of 3?
0011.
So this will be the instruction. Is it okay now?
Yes, sir.
Any other question, anyone? Okay, if there's no question, so let's move forward. Okay, we have got a few small things to finish up. At the beginning of this chapter, I left out one thing, that is the bit addressable RAM location, and I told you that we will discuss it at the end of chapter 5. So this is your bit addressable RAM. At this point, I will suggest all of you, if possible, try to open the soft copy of the book. I mean, it will help you. If possible, try to open the soft copy of the book. There is a figure which I will draw, but the figure is so cumbersome that even if I draw, you will not understand it properly. So I will suggest you try to open the book. Even if you are in mobile, you can open it, I think. Alright, so far, all the instructions that we saw were byte addressable, meaning that if you access a memory, you had to access all the bits of that memory. You had to access that memory as one. You could not separate that memory. So all these things, so far, whatever we have done, all these were byte addressable. But now we come in bit addressable. That means in a memory, we know that we have got 8 bits. So this particular location from 20H to 2F8, in this location we have got 16 bytes of memory, and these 16 bytes of memory you can access as a single bit. That means, okay, I'll draw a figure, don't worry. That means in each byte there are 8 bits, and if you want, you can access those individual bits as a single instruction or as a single memory location. Let me draw the figure, it will be much more clear. And those who have the book, you don't need to draw. You can see your figure 5.1. You can see your figure 5.1. I'll try to draw figure 5.1. Let me try to draw.
Excuse me, sir. So are the ports P1, P2, P3, 4, and 4 located in this bit addressable region?
No. But they are also bit addressable. You are right in that case. I got your question. They are also bit addressable, although they are not located in these addresses. Okay. That was your question, right?
Yes, sir.
All right, so this is just to give you the idea. As we said, from address 20 to 2F8 is our bit addressable. That means this address from 20 to 2F8, all these 8 bits has got separate address as well. You can see the address of this location is 00, the address of this location is 0B, the address of this location is 16, and so on. You should always remember this thing, that this is your digit 0, this is digit 1, D2, D3, D4, D5, D6, and D7. So how we can specify? Say if I ask you, where is 13 located? Your answer should be 13 is D3 in the memory location 22 hex. So if I tell you where is 0D, what will be your answer?
05 in memory location 20H.
D5 in memory location 21H. Why 28?
Oh, yes, sir, 21H.
Exactly. So if I say you where is 7E, your answer will be 7E is D6 in memory location 2FH. Did you understand how to find this thing?
Yes, sir.
You can also see table 5.2. I mean, those table 5.2 just gives you some examples of single bit instruction. Definitely, if you want to access this single bit, your instruction should also be a single bit instruction. Most of these instructions you already know, like set bit. Clear actually works with even bit or byte, doesn't matter. Clear works with everything. There are conditions like J bit, jump if bit. Then there are conditions like jump if not bit. So you will see all these instructions are summarized in table 5.2, where you will see some bit instructions. Let us now take an example, okay? And try to open the figure 5.1 of your book. Then it will be easier for you to solve the following example. This is example 5.11 of your book. So let us just solve a few. Say the first instruction is set bit 42H. The second is clear 67H. Try to answer this using the figure. Don't just say the answer which is directly there in your book. All right, so if this is the case in the first one, tell me where is this location stored? Where is 42H situated? 28H. You need to be more accurate. Which digit?
So D220.
Exactly. This is D2 of RAM location 28H. Similarly, where is 67H? Just look at the table. We figure 5.1.
Sir, D7 of.
Exactly. D7 of which address?
2CH.
Exactly. 2CH. And the last one?
So D7 of 21H.
Exactly. D7 of 21H. So see, these are actually very simple and very easy. Now the thing
Sir,
is,
the first one shouldn't be 25H.
25. No, I mean, if you open the figure and look for 42H. I think 42 is there in 28. Why 25? Not 25. All right. Now the important thing is this table that you are seeing in front of you, not table again and again, table, figure. This figure will not be provided to you during the exam. Try to understand that this figure is not very difficult. You need a few information, that is your starting address is 20. In each address you have got 8 bits. So all you need to know is you need to know how to count in hexadecimal format. So if you know how to count in hexadecimal format, whatever you are given, you can easily find out the digit and the corresponding address. I mean, if I give you the table that you have in front of you, and if I set questions like this, I mean, that does not make a question for 4th year students. So this table, again, I'm saying it is very easy. All you need to do is you need to know how to count in hex. If you know how to count in hex, you can easily identify where is it located. Okay, so any question up to this? Alright, there are a lot of examples which I will not go through, so this will actually go for your self-study. Please go through all the examples. You will understand the examples. It's very easy. Then please go to move X instruction. This small paragraph, it is nothing. I told you that you have provision to add extra RAM in your 8051, extra RAM or ROM memory space. There is provision where you can add this extra memory. So if you add this extra memory, we use move X instruction. Okay, that is the only thing that you need to know. So just go through that small paragraph. It is very easy. And the last thing that you need to go through is Article 5.4. This is also 1 or 2 paragraphs, very small. So please go through all these things. With this, our chapter 5 comes to an end. And of course, if you face any problem in these places, I will always be there. Don't think that I have not taught does not mean that I will not teach you. Nothing like that. Try to read on your own. I believe you will understand. Still, if you face problem, definitely I will explain you. Okay, so with this, our chapter 5 comes to an end. We still have one more week for the midterm. So let's see how much. Our target was to complete up to chapter 6. Let's see how much we can do. How much we can proceed in that midterm. Any question in today's class up to this? You know what is going to happen now. So if you have any question, you can ask now.
Sir, what is flash ROM?
Flash ROM. Where did you get flash ROM?
In an example. In example 5.6.
5.6.
Yes, sir. In the question.
So what actually burn in a flash ROM starting from the flash ROM is mostly external ROM because you can see the address starting from 408. So most of it is external ROM.
Okay.
Anyone else? Any other question? Okay, if you don't have any question, please get ready for a quiz. Turn on